This paper is about ordinary least squares regression in the setting where there's an adversary that can corrupt your training set in some very bad way. And this is joint work with Pravesh, Kothari and Raghu, Meka. So the setup is that we have a distribution D that's a joint distribution on RD cross 0, 1. I'm picking 0, 1 here for simplicity. It extends to other ranges. And I define this quantity opt, which is the error of the best fitting linear function W with respect to D. So it's the expectation of a draw from D x, which is x comma y, of W dot x minus y squared. So it's the square loss of the best fitting linear function. And then we have S, which is a training set drawn IID from D. And the goal in ordinary least squares here is to find some W prime, some other linear function whose square loss is very close to opt. So find a W prime whose square loss is competitive with the square loss of the best fitting linear function. Okay, and the difficulty here is that S is going to be corrupted. What do I mean by that? So if S is x1, y1 through xm, ym, where so each xi is drawn from is in R to the D, and each yi is in 0, 1. The adversary can go to S and corrupt an eta fraction of the points however she would like. So the adversary could remove an eta fraction of points. The adversary could change an eta fraction of points to, and the adversary is allowed to corrupt both the covariates, the x's, and the y's. So there has been some work previously on efficient algorithms for regression where only the responses yi's are corrupted. In this paper, we're going to consider the harder case where both the x's and the y's can be corrupted. And if you're familiar with the Huber contamination model, this is a more difficult setting. In the Huber contamination model, you're allowed to add noisy points, but you can't take away uncorrupted points. So here you can really corrupt S by affecting any eta fraction of points in whatever way you'd like. Again, the goal is still going to be to find some linear function whose square loss is competitive with the best fitting linear function from the uncorrupted true distribution D. Okay, so our results are, we're going to give the first set of efficient algorithms. So this is an intensely studied problem, but I'm not aware of any work that gives provably efficient algorithms for solving this problem. So we'll give the first set of efficient algorithms for solving this problem, and we'll need to take an assumption on the marginal distribution on R. And I'll talk more about the marginal the assumption in just a second, but in the back of your mind, you can think of it as that the marginal distribution satisfies some bounded moment condition. And we also prove that it's information theoretically impossible to solve this problem unless you take some sort of assumption on the distribution. So some sort of assumption is necessary. And what I'll point out on the next slide is that even solving this problem in exponential time is non-trivial. So even exponential time algorithms were not known. Okay, I should mention that there's been a lot of work recently on robust learning, typically in the unsupervised setting. For example, robustly estimating the mean of a Gaussian. And so it may not be surprising that there's some concurrent and independent work on this problem. In our setting, so the concurrent and independent work is for the case when y, the response, is actually equal to w inner product x plus some IID noise. So there are 3 papers here. I don't have time to read all the co-authors, but what distinguishes our work is that our setting doesn't require this functional relationship between y and x, so the distribution really is arbitrary. And we use a totally different set of techniques. So these works use tools from robust mean estimation, and our algorithms are derived from the sum of squares paradigm that's popular in theoretical computer science right now. Okay, so here's the key difficulty and the key idea that I want to get across in the talk. So let's assume that S, again, is your original training set, and S prime is the set that's been corrupted by the adversary. And consider the following naive strategy for solving the problem. I have S prime in front of me. I'm going to brute force search over all sizes of all subsets of size 1 minus eta times S prime. Sorry, that should be S prime. So I'm going to brute force search, looking for that subset of examples that have not been corrupted. Then I'll perform ordinary least squares regression for each one of these subsets. And I'll just output the W that I find that has the smallest square loss among all of these. And the reason why you might think this would work is that, well, surely one of these subsets is going to be a subset that has all uncorrupted training examples. That should have low square loss. And so I should be able to find such a W and just output it. The problem with this approach, and you can prove that this approach, we give examples where this approach fails in the worst case, is that the adversary could be very sneaky and corrupt S in such a way that you find a subset whose square loss is actually smaller than the square loss of the true linear function. Okay, so what we prove is that under an assumption on the marginal distribution, this strategy actually does work. And the assumption that we need to take is something called hypercontractivity. This assumption holds for a large class of distributions, including log-concave distributions, Gaussians, product distributions, non-spherical Gaussians. So it holds for a very general class of distributions. And the main lemma that we prove sort of encapsulates this key difficulty is that if you have two distributions, D1 and D2, and their total variation distance is at most eta, then the square loss of some linear function W prime with respect to D2, with respect to D1, is at most the loss with respect to D2 times 1 plus square root of eta, plus some other terms that are less important. So you should think of D2 as the uniform distribution over your corrupted set. D1 is the uniform distribution over your uncorrupted set. And this says that if you find a function whose square loss with respect to the corrupted set is small, then you've actually found a function whose square loss with respect to the uncorrupted set is small. Okay? And even better, the proof is simple enough to encode into this sum of squares proof system. So then the question becomes, how do we find a W prime that has small square loss with respect to that corrupted training set? Well, we can write a non-convex program that tries to find this good subset that we were using brute force search to find, and then take a semi-definite relaxation of this non-convex program to get a polynomial run-in time. And the reason why it works is because this lemma, this key lemma, actually can be encoded using this very simple proof system. You can actually prove that this semi-definite relaxation gives you a good solution. Okay, and so more technically what we do is output some W prime whose error is roughly 1 plus eta times square root of eta times opt, plus this other term here, expectation of W dot x minus y to the fourth times square root of eta. And I'll just say that our dependence on eta, this square root of eta, is optimal here. It's not clear if this next term is optimal. I'll stop there.
Thank you. Yes, questions? One over there.
Oh, it's a very simple example. I can show it to you after the talk. But it's a training set in 3 dimensions, and the adversary can kind of use its corruption power to make it impossible for you to distinguish if these points came from one distribution or another. Does it depend on what? You mean on eta? Yeah. Oh, exactly here. I mean, yeah.
Okay, more questions. Yes.
When you say this works for log-concave distributions, do they need to be actually certifiably log-concave?
Yes. Actually, certifiably hypercontractive.
All right. Okay. Let's thank again the speaker, and thank you.